Students, welcome to another session of All4 e-learning program. Now in this session, we shall now take the applications of the electric field intensity due to a dipole at any general point. Let us deal all the cases regarding the electric field intensity due to a dipole at any point, whatever point he gives you. So it is applications of electric dipole at any point, at any general point, right? Let's take the things like this. So in the previous session we have evaluated the formula for the electric dipole, minus q plus q. This is the dipole. So midpoint, this is A, this is A. Mind you, this is a short dipole. So for a short dipole, right, so the dipole moment is 2aq, magnitude of the dipole moment is 2aq, like this. This is the dipole moment. So for an electric dipole at any arbitrary point, consider a point P, distance d, let's say, making an angle theta with the dipole axial line, making an angle theta with the axial line. So this is the radius vector actually, point P. Then we have evaluated a formula for the electric field intensity. We got the resultant electric field intensity at this point P. Let's say EP in general, it is 1 by 4 pi epsilon naught P by the distance of the point of concentration is D. It's P by D cube under root of 1 plus 3 cos square theta. This is the magnitude of the resultant electric field intensity at any point. For any point for an electric dipole, the electric field intensity is 1 by 4 naught P by D cube root 1 plus cos square theta. Now, on what factors does this depend? Again, now if this dipole is in air, so this is the electric field intensity. Had it been in a medium, in any medium, then it's 1 by 4 pi epsilon naught. You know, in the medium the permittivity is in air vacuum free space, the permittivity is epsilon naught, absolute electrical permittivity of free space. In any medium it is just epsilon, it is epsilon. But we know epsilon is epsilon naught k. K is dielectric constant. So we have learned relative permittivity or dielectric constant is epsilon by epsilon naught. So epsilon, I can write it as epsilon naught into k. So in a medium it is epsilon, that is epsilon naught into k, P by D cube under root 1 plus 3 cos square theta. Now, on what factors does this electric field intensity depend? What factors electric field intensity depend for at any general point, arbitrary point? First, the electric field intensity directly proportional to P. So first point, E directly proportional to P. So simply E1 by E2 is P1 by P2. The stronger the dipole moment, the stronger will be the field at that point. The more the dipole moment, more the electric field. So E directly proportional to P. Second, E inversely proportional to dielectric constant. It is a known thing. Force experienced by any charge due to another this thing in the presence of the medium is always k times less, right? K times less than the force in air. So it decreases k times. It is inversely proportional to k. So E1 by E2 is k2 by k1, or E1 k2 is E2 k1. It's a one thing. Next, the electric field intensity is inversely proportional to the distance. Third factor, it is inversely proportional to cube of the distance of the point. This is inverse cube law. The electric field intensity obeys inverse cube law. So this is E1 by E2 is equal to D2 cube by D1 cube. It is inverse, or I can write as E1 D1 cube is equal to E2 D2 cube. The electric field intensity variation with distance, ED. Now, it also depends on the angle theta made by the radius vector with the axial line. It also depends on the position of the point P. What angle does the radius vector make with the axial line? Right, theta, it also depends on theta. So the factor varying theta is E directly proportional to under root of 1 plus 3 cos square theta. Suppose if I consider two different angles, then E1 by E2 is under root of 1 plus 3 cos square theta 1 by under root of 1 plus 3 cos square theta 2. This is the ratio, right? It is directly proportional to 1 plus 3 cos square theta under root. So E1 by E2 is equal to, for two different, same distance, same dipole, same distance, same dipole P. P is same, distance is same, medium is same, but the angle made by the position vector is different. Let's suppose one make an angle 30 degrees, other make an angle 60 degrees, then field changes. For the same dipole, that is, suppose if I consider a dipole like this, one point is here, let me consider a circle. If I imagine a circle like this, so from this point, right, this point makes a small angle, this point makes a bigger angle. You see, it is for the same dipole P and same distance, circle, the radius of the circle is same, distance is same, but angles are different. Now the field varies from this point to this point, right? If it is at this point, it is still different. This way it is. So for the same distance and the same dipole, for different angles, the electric field differs. So electric field intensity with the angle also. Considering all these things, putting all the things in one entity. So E1 by E2 is, first it is dependent on dipole moment P1 by P2. Second, it is inversely proportional to dielectric constant K2 by K1. It is inversely proportional to distance d2 cube by d1 cube into this under root of 1 plus 3 cos square theta 1 by 1 plus 3 cos square theta 2. This is the ratio, comparison of the electric field intensity at two different points for a dipole at any point, arbitrary point in the field of the electric dipole. So E1 by E2, P1 by P2, K2 by K1, d2 cube by d1 cube, root 1 plus 3 cos square theta 1 by 1 plus 3 cos square theta 2. So these are the mathematical applications of the electric dipole at any arbitrary point with respect to its magnitude. Next, now let us now evaluate the direction of the electric field intensity and what are all the various applications regarding this. There were some previous entrance questions based on the angle, based on the direction of the electric field intensity. So I just wanted to give it in clear. Yes. So now let us take up the direction of the electric field intensity and the applications of it. If I consider an electric dipole, this is minus q, this is plus q, and the dipole moment is p. This is the short type. Consider any point P here, the arbitrary point P at a distance t from this center of the dipole. Now let the radius vector of this point make an angle theta with the dipole moment of this dipole. Now, so at that point, what is the direction of the electric field intensity there? You know, in the previous episode, we have considered this dipole as a combination of two dipoles. So this is split into components like this. I have cut into two components. One component along this and other perpendicular component like this. So this is P vector, P, it was split into components. This is component along with the angle, that is P cos theta. This is the component perpendicular to the first one, this is P sin theta. So the electric dipole was imagined to be the combination of two dipoles like this. So it is like two dipoles existing at the point O, right? At the point O, and the resultant here we have to find. And you know, we have considered first we have considered this dipole. So at this point, due to this dipole, that is P cos theta, the point P lies on its axial line. So the electric field intensity E1, this is E1, and we got the formula E1. The point P lies on the axial line of this dipole. On the axial line, we know the formula is 2p by d cube. So it is 2. The dipole moment of this dipole is p cos theta, 2p cos theta. Distance of the point is d, it is dq. So the electric field intensity at that point due to this dipole is 1 by 4 pi epsilon 2p cos theta by dq. Right? The direction of this electric dipole on the axial line, we know the electric field intensity is parallel to the dipole moment. So if this is the dipole moment, then the electric field intensity is like this. First one. Next, considering this dipole, second component, p sin theta. Due to this dipole, the point P here, the point P lies on its equatorial line. So for this dipole, it is the equatorial line. Right? So for the first dipole, if this is the first component, then this point lies on its axial line. For the second dipole, when I consider like this, the point P lies on its equatorial line. So on the equatorial line, the electric field intensity E2. We know on the equatorial line, the electric field intensity is 1 by 4 epsilon P by d cube. P. So our component is P sin theta. So it's 1 by 4 pi epsilon naught P sin theta by dq. This is the component. And you know the direction of the electric field intensity due to the dipole on the equatorial line. It is parallel to the dipole moment but in opposite direction. So this is the dipole moment and in opposite direction it is like this. This is the resultant electric field intensity, that is E2 it is at point P. Now at this point, the resultant electric field intensity due to these two, will lie in this direction. This way it is. So if I consider the resultant electric field intensity, this is the axial component, the electric field due to P cos theta E1, and this is E2, right? If I consider these two as two sides of a parallelogram like this, then the resultant vector, this is the resultant vector, right? So the resultant electric field intensity will be in this direction for this. Let this resultant electric field intensity make an angle alpha. The electric field intensity make an angle alpha. So our point of consideration was making an angle theta with the axial line of the original dipole, and let the resultant electric field intensity make an angle alpha with the component, P1 component. Then considering this right angle triangle, right, let me take this parallel to it here. So this is E2 and this is E1. So therefore E2 parallel to it and this is E1. Now from this right angled triangle like this, tan alpha is equal to, considering this as a right angle triangle, the adjacent component is E1, the perpendicular component is E2. This E2 I can imagine here. So perpendicular component, both are perpendicular, so even here it is also perpendicular. So this becomes a right angle triangle. Tan alpha is equal to E2 by E1. It is mod E2 by mod E1. So it is the ratio of opposite side. Tan alpha is opposite side to adjacent side, mod E2 by E1. Now substituting, tan alpha is equal to E2. It's 1 by 4 pi epsilon naught P sin theta by d cube by E1. It's 1 by 4 pi epsilon naught P cos theta by d cube. So the direction of the resultant electric field intensity at the arbitrary point, right? This is the resultant electric field, and which is making an angle alpha with one of the component, with the radius vector. So therefore E2 makes alpha. So tan alpha is perpendicular component by adjacent component, E2 by E1. E2 is due to P sin theta, so it's P sin theta by d cube. E1 is 2P cos theta by d cube. 2P cos theta, it's 2P cos theta by d cube. 1 by 4 is not 2P cos theta by d cube. So simplifying, this cancel, P cancel, d cube cancel. So therefore tan alpha is equal to sin theta by cos theta 1 by 2. So it's sin theta by 2 cos theta. But according to trigonometry, I can consider sin by cos is tan. So it is tan theta by 2. So therefore the direction of the resultant electric field intensity at any arbitrary point makes an angle alpha with the radius vector, the radius vector point of concentration. So then tan alpha is tan theta by 2. So putting this in the actual figure, tan theta by 2. So our actual dipole was, this was the dipole, minus q plus q, and this is the dipole moment P. Our point of concentration, this is the midpoint of the dipole, and this is the radius vector. This is the radius which was making an angle theta. So it is the actual dipole P, axial line of the dipole, axial line of the dipole like this P. So now the resultant electric field intensity, now let us forget the components even. The resultant electric field intensity makes an angle alpha with the axial line. Now considering both, what is the direction of the resultant electric field intensity with the axial line of the dipole? If I take the total angle with the dipole, now this angle is alpha, and from there it is, sorry, this angle is theta, and from there it is alpha. So the net direction, so the total angle made by the resultant electric field with the axial line of the dipole, with the axial line of the dipole, the total angle is theta plus alpha, where theta is the angle made by the radius vector, and with this radius vector the resultant field makes an angle alpha. So if I extend this like this, then the direction of the resultant electric field at any arbitrary point with the axial line, with this axial line, this is theta plus alpha. So this is theta plus alpha. This was a previous entrance question. In one of the entrance examination, it was asked the resultant electric field intensity at any arbitrary point in the field of the electric dipole, it makes an angle, right? The angle of the radius vector is theta, and the angle of the electric field with the radius vector is alpha. So the total angle is theta plus alpha. So combining these both, alpha, so we got tan alpha is tan theta by 2. From this we can evaluate alpha is equal to tan inverse of tan theta by 2. Tan inverse of tan theta by 2. So therefore putting the total angle here, so the direction of the resultant electric field at any point due to an electric dipole, the direction is theta plus alpha, that is theta plus alpha is tan inverse of tan theta by 2. Tan inverse of tan theta by 2. So this is the net resultant direction, the angle made by the resultant electric field due to an electric dipole at any arbitrary point. Theta is the angle made by that point by the radius vector with the axial line, and alpha is the angle made by the resultant electric field with that radius vector. So the total angle is theta plus alpha, or it is theta plus alpha is tan inverse of tan theta by 2. So therefore it is like this. So this is the direction. So net direction, resultant direction of the resultant electric field. Let us say this is beta. So beta is theta plus tan inverse tan theta by 2. Right? Okay. This is regarding the direction of the electric field intensity. And suppose if you consider the magnitude of the electric dipole, third one, consider an electric dipole. This is an electric dipole, this is minus q, this is plus q, a short electric dipole of dipole moment P. Then at any arbitrary point we have evaluated the resultant electric field intensity. The direction will be like this. This is theta and this is alpha. Then the resultant electric field magnitude is 1 by 4 pi epsilon naught. It's P by, if the distance is r, P by r cube 1 plus 3 cos square theta it is. 1 plus 3 cos square theta. Now let us take up the conditions. First, had this point been on the axial line itself, instead of this point, instead here, if this point had been at this point on the axial line, so if the point P, instead of here, if it is at this point, it is on the axial line, then the radius vector will make an angle 0 with the axial line of the dipole. So if I imagine this point to be at this point, then the angle theta is 0. Now if I substitute 0, so if the point P lies on the axial line, point P is on the axial line, then the angle made by the radius vector with the axial line becomes theta 0. So therefore its electric field intensity is 1 by 4 pi epsilon naught P by r cube root 1 plus 3 cos square theta, cos square 0. We know cos 0 is 1. So the resultant electric field intensity is 1 by 4 pi epsilon naught P by r cube root 1 plus 3 into 1 3. So the resultant electric field strength is 1 by 4 pi epsilon naught P by r cube root 4 it is 2 P by r cube. This is the electric field, we have evaluated earlier. This is the electric field on the axial line. So it is the maximum value due to the maximum value of the electric field intensity due to electric dipole at a particular distance d. For the fixed distance d r, then the maximum value of the electric field intensity is 2p by d cube. It is on the axial line of the magnet. Yes. So according to the electric field intensity at an arbitrary point, the field intensity is maximum on the axial line for the particular distance. For a particular distance r, it is maximum on the axial line, right? Suppose if the same thing had this point be on the equatorial line. So if the point P, if I imagine on the equatorial line, so let the point P, point of concentration P is on, it is on the equatorial line of the dipole. Then, so if it is on the equatorial line, then the radius vector makes an angle 90 degrees. So then theta will be 90 degrees. Theta is 90. So therefore, substituting theta 90, the magnitude of the electric field intensity is 1 by 4 pi epsilon naught P by r cube under root 1 plus 3 cos square 90. According to trigonometry, cos 90 is 0. So cos 90 is 0. So it becomes electric field intensity is 1 by 4 pi epsilon naught P by r cube. It's root 1 plus 0. It's root 1 into 1. So simply P by r cube. Right? So it is the electric field intensity on the equatorial line. We have evaluated earlier. Right? Same thing. So it is a general formula. Right? You need not take separately for axial line, for equatorial line. You need not remember the things. Just remember the single formula. The electric field intensity due to electric dipole at any arbitrary point. Short electric dipole at any arbitrary point. 1 by 4 naught P by r cube root 1 plus 3 cos square theta. If the point is on axial line, put theta 0. Cos 0 1. 1 plus 3 root 4. Root 4 is 2. 2 P by r cube. Maximum. If the point P lies on the equatorial line, cos 90, theta, equatorial line angle is 90 degrees. Cos 90 is 0. So cos 90 is 0, it is P by r cube. Minimum. And for this particular distance, this value is minimum. So for an electric dipole, if I consider an electric dipole like this, minus q plus q, right? On the axial line, the electric field is strong. So the lines of force will be dense. Actually, the lines of force are dense there. So strong electric field. For the same distance here, the electric lines of force are rare. They are far apart. So the field will be weak. So on the equatorial line, the electric field intensity is minimum. For the same distance, it is minimum. Right, this way. So the electric field intensity due to arbitrary point. So in general, suppose if he has asked you to find out the ratio of the maximum to minimum electric field intensity due to a dipole at a particular distance r, maximum to minimum intensity due to electric dipole at a particular distance r. Like for example, suppose if I imagine a dipole like this, minus q plus q, this is the dipole moment. So for the same distance, imagine a circle around this. Imagine a circle around this. For the same distance r, radius of the circle is r. Radius of the circle is r like this. Right. Then what is the ratio of the maximum to minimum electric field intensity due to dipole? at any point. We know the field is maximum on the axial line. So it's 1 by 4 pi epsilon naught, it's 2p by r cube. And the field is minimum on the equatorial line. So it's 1 by 4 pi epsilon naught p by r cube, dividing it's 2:1. Here the field is twice the electric field due to this point. The field is twice the electric field due to this point. So E max to E min is 2:1. On the axial line it is maximum, on the equatorial line it is minimum, right? So for an electric dipole at any arbitrary point, the electric field intensity, magnitude of the electric field intensity, the magnitude of the electric field intensity at any arbitrary point, 1 by 4 pi epsilon naught p by r cube root 1 plus cos 3 cos square theta. And the direction of the electric field intensity, direction, angle made by the electric field intensity beta is theta plus alpha, that is theta plus tan inverse of tan alpha by 2. Tan inverse of tan alpha by 2. So this is the angle made by the resultant electric field intensity like this. So it's tan theta plus alpha like this, right? Now sometimes he'll be asking you to compare the angle. For example, there is a question was asked like this: for an electric dipole, if I consider an electric dipole like this, right? Consider an electric dipole at the origin of a Cartesian 2D system. Origin of the Cartesian 2D system. This is the dipole moment P. So this is at 0, 0. Now he is asking you to find the electric field intensity due to this electric dipole, short electric dipole at a point P, A comma B. At a point P, A comma B. He has given the coordinates of the point in this Cartesian system, coordinates of the point. So we know if this is 0, 0 and this is A comma B, the radius vector, the magnitude of this R, the radius vector, this is root of A square plus B square R. Because you know, if I drop a perpendicular, this is A and this is B. So therefore R is root of A square plus B square. So the distance of the point P from the origin, the distance of the point P from the origin R, it is R. At that point, what is the electric field intensity? So the electric field intensity, resultant electric field intensity at any point P. Imagining the dipole at the origin and the point P is A comma B, when the magnitude is 1 by 4 pi epsilon naught, he has given the dipole moment P. Let the angle made by this dipole with the made by the radius vector with the dipole be theta. So we know the general formula for the resultant electric field intensity is 1 by 4 pi epsilon p by r cube under root 1 plus 3 cos square theta. Now substituting. So resultant electric field intensity is 1 by 4 pi epsilon naught p by R. R is this distance. R is root of A square plus B square. R cube it is. So it is root of A square plus B square whole cube. Under root of 1 plus 3 cos square theta. Now he has not given theta there. He gave you just the coordinates. So we have to evaluate, we have to find the angle. You know, when I drop a perpendicular from here to here, this distance is A and this distance is P. This is a right angle triangle. Now from this, please find what is cos theta. Cos theta is adjacent by hypotenuse. So it is A by R. So cos theta is equal to, it's A by under root of A square plus B square. So substituting this at this point. Substituting this there. So therefore, the resultant electric field intensity at an arbitrary point in the Cartesian plane A comma B, for the coordinates A comma B, it's 1 by 4 pi epsilon naught. Dipole moment of the dipole is P. Distance of the point is A square plus B square. So it is A square plus B square whole power. It is 3 and the root is 1 by 2. It is 3 by 2. Under root of 1 plus 3 cos square theta, I have got cos theta is a by r. So this is a by root a square plus b square. So it is a by under root of a square plus b square whole square. So evaluating, simplifying the things, it's 1 by 4 pi epsilon naught p by a square plus b square whole power 3 by 2 under root of 1 plus 3a square by a square plus b square. So squaring a square by a square plus b square. So it's 3a square by a square plus b square. You can take LCM and still further simplify the thing there. So this electric field intensity 1 by 4 pi epsilon naught p by a square plus b square whole power 3 by 2 under root of, it is taking LCM, here it is a square plus b square under root, so a square plus b square plus 3a square. Still further simplifying, 3a square plus a square, you will get 4a square. Denominator a square plus b square under root can be added to it. You can add to this. Now that when you add to this one, a square plus b square whole power 3 by 2 into a square plus b square whole power 1 by 2. So that becomes whole square. So a square plus b square whole square. Numerator you will get 3a square plus a square, that is 4a square plus b square. So that way you can find the electric field. Simplify that. Thank you.